Hello. In this video, I'm going to introduce this concept of acceleration, which is not always easy to understand. So acceleration, by definition, is the rate at which you're changing your velocity, not your speed, but rather your velocity, which means you can have acceleration by changing your speed, okay, or by changing your direction, because velocity is both speed and direction. So let's take an example, a car, okay. You can accelerate / decelerate in the car using three things in the car. You can use the gas pedal, that will give you some acceleration, okay? So it's going to make you speed up. You can use the brake pedal, that's going to make you slow down. That's also acceleration. We just happen to call it deceleration. But you can also use the steering wheel, okay? So when you're using the steering wheel, you can be going at 25 miles per hour, but the fact that you're turning means that it's got to be some acceleration. And we'll talk about this later. Let me just make sure I'm recording. Yeah, we'll talk about this later when we do forces, that the fact that you're turning, it's got to be a force acting on you. And if there is a net force acting on you, there's got to be some acceleration. And we'll talk about that in a later unit. So just remember that acceleration can mean changing speed, changing direction, or both. You can have both. You can be going around the curve, slowing down, but also turning, or speeding up around the curve. So acceleration, we're going to do it in one dimension. So acceleration, average acceleration that is the change in velocity over time. Okay? So if I go from 30 meters per second to 40 meters per second in 2 seconds, then I do 10 divided by 2. Do not confuse acceleration with speed. So in other words, you can have an truck going from 50. So the definition of acceleration, or the formula, is acceleration is how fast you change your velocity. So if it's in one dimension, it's just the change in speed over time. Okay? And when we change direction, we'll talk about some other stuff. So I have an example here. A car is going from 50 to 60 miles per hour, and it takes 2 seconds to make that change. Let's compare that to a car going from 10 to 20, but it takes 1 second. Now, do not confuse acceleration with how fast you're going. It's how fast you're changing. So here you made a change of 10 in 2 seconds. Down here you made a change of 10 in 1 second. So the acceleration is bigger in the second case. Okay? All right. The other thing I want to talk about is, since we say that acceleration is the change in velocity over time, so if we have a velocity time graph, the change in velocity over time is basically just the slope in a velocity time graph. So this is going to be the slope in a VT graph. Okay. Now there's something also that's important you can get from a VT graph, and we'll talk about it a little bit more in class. Is if you can find the area, okay, between the velocity curve, it has to be a velocity time graph, and the time axis, that's going to be your displacement. Okay. Now, if you have it down here, and if you find the displacement, you look at that displacement as a negative value. All right? And that's it. See you later. Okay. Guys, today we're going to talk about acceleration. It says review, but there are some new things in here. It's not just a review, but a lot of what you're going to see here is a review, at least for today's lesson. So we have to fill in these blanks here. And I want to try to figure out the relationship between the direction of motion and the direction of the acceleration vector, right? So I'm not going to fill in the blanks yet, but I'm going to look at different scenarios and see if we can come up with a pattern. So the first scenario is like I'm going to be going to the right with an initial velocity, VI. The I stands for initial. And then I'm going to speed up, which means my final velocity, which is VF, is a longer vector. And in order to find the acceleration, you have to find the change in velocity over time. Okay. Now, time is positive, okay, which means it does not affect the direction of the the change in velocity vector, okay, which is Vf minus Vi. That's added as vectors or subtracted. So since delta t is positive, okay, delta V and A would be in the same direction. So basically, if I find the direction of delta V, that's the same as the direction of A. So let's try this. So I'm going to add or subtract these two vectors graphically. Okay. So to find the change, you do Vf. You come to the tip of Vf and you subtract Vi. So Vi is going here to the right. Over there, it's going to be going left. And the delta V is basically the resultant. And that's going to connect the very first origin to the last arrowhead. So delta V is going to the right, which means, based on what I just said earlier, the acceleration will be going to the right. And I'll do the same thing for an object that's slowing down, but still going right. So Vi is to the right, and Vf is smaller, and it's still to the right. So I'm going to do Vf, which is right here, come to the tip of Vf and draw negative Vi. This is negative Vi, by the way. Negative Vi. And the change is to the left. Okay, so which means acceleration is also to the left. And then I'm going to do the case where we're going left and we're speeding up. So the Vi is smaller than the Vf, but they both go into the left. So my Vf is going left. I come to the tip of Vf and I draw the opposite of Vi. That's the opposite. So my delta V, or the resultant, is right there. So which means the acceleration is going left. It's the same direction as delta V. Then I'm going to look at the next case where I'm starting with a high speed and I'm slowing down, but I'm doing it in the negative direction. So here is my Vf. And then I'm going to come here and do the opposite of Vi. And combination or the resultant is this delta V, which is going right. Okay, so it's like this. So let's try to see if there is a pattern here. I'm speeding up, okay, to the right, and the acceleration is to the right. I'm slowing down to the right, okay, the acceleration is to the left, okay, and here I'm speeding up to the left, and the acceleration is to the left. And here I'm slowing down to the left, and the acceleration is to the right. So the pattern is this. Whenever you are speeding up or accelerating, right, the acceleration is in the same direction as motion, or in the same direction as the velocity vector. When you're slowing down, the acceleration and the direction of motion are opposite. Okay, so we have to fill in this. So when an object slows down, the acceleration is opposite. Okay. When an object speeds up, its acceleration is in the same direction. Okay, let's get rid of it. It's the same direction of motion, right? So this is basically kind of like explains that shortcut that I gave you a while back. If it says if an object is slowing down in the positive direction, the acceleration is negative. That's where that comes from. All right, so let's look at this conceptual question. So we're going to try to do this without a calculator. And I'm not going to write anything down. I'm just going to talk. All right. So the first one says a car entering a freeway accelerates at 2 meters per second, which means it gains 2 meters per second every second. The car is traveling north, okay? And it's speeding up. So it's going from 8 to 28 north, okay? Now, how long will it take? Well, you need to change by 20 meters per second. And you're doing that at a rate of 2 meters per second every second. So you need 10 seconds to get that done. Okay? What is the direction of the acceleration? Well, the car is going north, right? And you're speeding up. And we learned earlier that if you're speeding up, the direction of travel and the acceleration vector are in the same direction. Okay, that's that. So you can take that and write it in proper English. Ball A is thrown downward with an initial speed of 5 meters per second, so you throw it down. Okay? Ball B is thrown up with an initial speed of 15, so you throw it up in the air with 15. So the first one is like this. You throw down, right? The other one you just throw it up with 15. Now, the question is asking which has a greater acceleration. We don't care about the sign. We just want to know which one creates a bigger change in velocity. And we need to explain. Now, we're talking about this problem after the ball leaves my hand, either way, right? So if you think about this, the acceleration should be the same in both cases. Because once the ball leaves my hand, either on the way down or if I throw it up, the only thing acting on it is gravity. And gravity does not know the difference between an object moving down and an object moving up. It acts on them the same exact way. And that explains number 3. They're similar. Before an airplane cruises at a steady 20 meters per second, and a person jogs at a steady 4 meters per second, which has a greater acceleration? Well, neither one of them. They don't have any acceleration because you're going at a constant speed in both cases. Two cars start from a red light and speed up onto a freeway going 30 meters per second. Car E reaches its cruising speed in 4 seconds. Car F reaches its cruising speed in 8 seconds. Which has a greater acceleration? Well, the car that gets up to speed faster has a greater acceleration. So car E does it in less time, so the acceleration there is bigger. So in other words, it changes quicker, changes its velocity quicker. A car moves to the left and slows down. So it's moving left, slowing down. So you can see that the acceleration will be to the right. Okay? In which direction is the car moving? That's a silly question. It tells you right here that it's moving to the left.